Energy balance, or the first law of thermodynamics for any system undergoing any process, is revealed here. Delta E is the change in a system's total energy during a process. It is the sum of the changes in its internal kinetic and potential energies. Note that energy is a property, and the value of a property does not change unless the state of the system changes. Delta U denotes the change in internal energy. For specified initial and final states, the values of the specific internal energies can be determined directly from the property tables or thermodynamic property relations. Delta Ke represents the change in kinetic energy. And finally, delta Pe is the change in potential energy. Most systems encountered in practice do not involve any changes in their velocity or elevation during a process. Thus, for stationary systems, the changes in kinetic and potential energies are zero, and the total energy change relation in the previous equation reduces to delta E equals delta U for such systems. Also, a system's energy during a process will change even if only one form of energy changes, while other energy forms remain unchanged. Let us move back to the previous energy balance equation. It can be used in the rate form, as shown here. For constant rates, the total quantities during a time interval delta t are related to the quantities per unit time. The energy balance can be expressed on a per unit mass basis as follows. Now let us move to the mechanisms of energy transfer in the energy balance equation. Energy can be transferred to or from a system in three forms: heat, work, and mass flow. Energy interactions are recognized at the system boundary as they cross it, and they represent the energy gained or lost by a system during a process. The net transfer of energy in heat, work, and mass equals the difference between the amounts transferred in and out. The energy balance can be written more explicitly as shown here. The subscripts in and out denote quantities that enter and leave the system, respectively. The direction of any energy transfer is described by the subscripts in and out as well. The heat transfer is zero for adiabatic systems. The work transfer is zero for systems that involve no work interactions. The energy transport with mass is zero for systems that involve no mass flow across their boundaries, usually for closed systems. For a closed system undergoing a cycle, the initial and final states are identical, and thus delta E system equals the difference between E2 and E1. Then, the energy balance for a cycle simplifies to E in equals E out equals 0, or E in equals E out. Noting that a closed system does not involve any mass flow across its boundaries, the energy balance for a cycle can be expressed in terms of heat and work interactions as presented. For simplification, the directions of heat and work interactions are assumed as follows. Heat to be transferred into the system in the amount of Q, and work to be done by the system in the amount of W. Therefore, the energy balance relation in that case for a closed system becomes as the following. To comprehend this, let us discuss the following example. In this problem, saturated water vapor in a piston cylinder device expands at constant pressure due to heating. It is to be shown that delta U in the first law relation can be combined into one term, delta H, for a constant pressure process, and the final temperature is to be determined. Before we solve the problem, we must first specify assumptions for simplification as presented here. Three systematic steps can be used to determine the specified problems as described here. For step 1, we must first establish the number of states and the process involved. Based on example 4.5, the system undergoes a heating process at constant pressure that consists of two states. Then, determine the phase of each state based on the state postulate. Establish two intensive independent properties, and use the 5 steps rule of thumb. First, we sketch a saturation line on a suitable property diagram that includes all the necessary given properties. Then, we establish each axis of the diagram based on the given information. For example 4.5, we will sketch a PV and pH diagram simultaneously because it could help us solve the given problem. In this example, we will use property table A5 that lists H2O properties under pressure. Since we know the system consists of two states, we must determine both states' phases and show them on the PV diagram. Please note that the phase of any states can only be determined through the state postulate. It means we should first establish two independent intensive properties for each state before determining the state's phase. On the PV diagram, we draw the corresponding saturation temperature constant line for state 1 at 300 kilopascals. Based on table A5, the corresponding saturation temperature is 133.52 degrees Celsius. The initial state, or denoted as state 1, exists in saturated vapor. Therefore, state 1 rests on the point as demonstrated here. Then, we determine the related states properties through the properties table as demonstrated. Based on this example, we do not know another independent intensive property of the water for state 2. This can be determined by comparing a suitable property to the saturated liquid and saturated vapor values. From the information given, we can determine the specific enthalpy directly from the energy balance equation for a closed system undergoing a quasi-equilibrium constant pressure process. The direction of heat transfer can be specified to the system, and the work to be done is by the system. The work interactions are the sum of boundary and other work forms, such as electrical and shaft. For a constant pressure process, the boundary work is given as W boundary equals P multiplied by V2 minus V1. Also, H equals U plus PV. The equation reduces to the following form. Substituting the heat and work values into the relation, H2 becomes 2864.9 kJ per kilogram. The value of H2 is higher than Hg. Therefore, state 2 exists in a superheated vapor phase as illustrated. Now, the final state is entirely specified since we know both the pressure and the enthalpy. Constant pressure process curve is sketched on the PV diagram as demonstrated. The boundary work and the change in internal energy in the first law relation can be combined into one term, delta H, for a constant pressure process. It has been explained during specifying state 2. The temperature at this state can be obtained in table A6 at 300 kilopascals or 0.3 megapascals. The enthalpy of state 2 is 2864.9 kilojoule per kilogram, which rests in a superheated vapor. Based on table A6, this enthalpy value lies between two enthalpy values. The corresponding temperatures of those enthalpies are 150 and 200 degrees Celsius respectively. By linear interpolation, it is determined to be 199.5 degrees Celsius.